I was talking about the Higgs and T-quark phases and the fact that above the critical point, things become very different with no Higgs and no particle masses. So with no particle masses, your Kobayashi-Maskawa matrices really don't exist, except as a very democratic thing, and that's what Marni does.
Yeah, so that's where mixing becomes like equal in every...
Totally democratic matrix.
Yeah, so this is a democratic matrix. Yeah. Which is nothing like what we actually observe. Well, the one we actually observe for quarks is roughly like an identity, very different from this one.
Once you get down below the critical point into the so-called normal region, which is really a complicated region, the simple 11111 gets all muddled up because the T quark is a different mass from the B quark, and all the other quarks have different masses, and you have all kinds of things. You can calculate a Kobayashi-Maskawa matrix.
So we want to get the parameters from the geometry.
Yeah, but the way I have to do it down here is use the masses and mass ratios, and it comes out pretty close.
Yeah, it's close to connect.
But that's because we got the ugly mass stuff to work with, and this is the stuff that I strongly object to the interpretations of the laboratories. Fermilab says those two green peaks do not exist. I think that's ridiculous. And CMS says, oh, the red line is not right. It should be a really fuzzy black line. When they got to the really fuzzy black line, or black forest of lines, by using narrow bends that were too narrow for the data set they had. If you use a proper 10 GeV bend instead of a 5 GeV bend, it comes out nice and smooth and exactly tracks the background. And the fact that it exactly tracks the background is an indication that the 10 GeV is realistic and the 5 GeV is not. Then we were talking about integrating out the CP2 gives you the Higgs mechanism that Meinhard Meyer and Andre Troutman and others did a long time ago. And that was done basically like this. This is a quote from the Meyer's paper showing how when you break from a total symmetry of a whole volume like that down to just part of it, you wind up with the Higgs left over. And it's the calculations are too complicated to put in a presentation like this. But it all works out very nicely and is based on a result from the book by Kobayashi and Maskawa. Kobayashi Nomitsu. And their book shows how to do that. It turns out that you not only get the existence of the Higgs, you get the Lagrangian structure that is characteristic of it also. Everything works exactly up to the signature of the Ginzburg-Landau potential. This just tells again about the three generations. First generation being Octonians, the second generation involving things that are partly in CP2. There are pairs of Octonians and things that started out propagating entirely in CP2 but have to be projected down to M4. You wind up with triples of Octonians. And that means that you need to do this way. You can do the quarks according to Octonian basis elements. You can do that. And a nice way to tie that into braid work, like Marni does, is to look at Lou Kaufman's description of the Octonian basis elements in terms of ribbons. And she knows more about that than I do.
Yeah, so in 2010 or so, Hackett and Kaufman found a way to represent the 8 units of the octonions in using exactly these diagrams, so that when you compose them, which is what I was talking about before, you're actually respecting the multiplication rules for the octonions with the non-associativity. So that works, that works very well. But to get braiding, we want to put this into structures with braiding where we have this rich class of representations, and that's only going to happen in 3 dimensions where you can actually braid things. But we're naturally picking out 3 and 4 dimensional pieces from higher dimensions, so we can do that in a very natural way. So, for example, we're picking 3 units IJK, and we can have braids with 3 ribbons, which is how I've got a picture of this braid representations for the particles. These pictures from Thompson. So this is 2005, where he characterised, I haven't drawn them all here, but it gives you an idea for how you can draw the rest of them. You characterise each state by 3 strands, and then each strand can be twisted, which is just denoted here by a sign. So these are the twists which would appear in Octillion diagrams as well, although we're combining these different pictures together in a category which does braiding and looping and twisting.
So when you go to the second generation, it has pairs of octonions, which are pairs of these guys, and there are 8 of these guys, so there's 64 pairs, and here they are. And I have some combinatorial rules I use, which I'm not going to go into them, but I'm going to say the combinatorial rules say that just one of these guys is going to be the neutrino, and only the muon is going to be just a few of them. Then you have the strange and charm quarks, and they have others of the pairs. Turns out that you wind up with more things fall into the charm quark category than into the strange quark category. So the charm quark and strange quark have different masses, and that is a nice combinatorial thing. I won't go into the details because it'd take too long. I've talked too much already. Anyway, that is where the difference in masses between the charm and strange and truth and beauty quarks come into play. You don't have it in the first generation because they're all just the same. And it turns out the first generation quarks up and down are same mass. And go to the third generation, you have 512 of 8 times 8 times 8. And again, only one of them is a tau neutrino, and 7 of them are tauons, but 7 of them are also beauty quark, and 161 are truth quarks. And the combinatorially, that's why the truth quark is so much heavier than the beauty quark. And for example, all these guys would correspond to one of the 3 colored red, blue, or green truth quarks. And that explains, it is the only explanation I've ever really seen, why the masses of the quarks are so different as you go up in generations.
So what we're doing, so this is one generation, and what we're doing is putting these together into like a closed diagrams, like in trefoil knots.
Yeah.
Where you're encoding the 3 generations in all the Jordan algebra information that's attached to the diagrams.
And that's a different thing from what I'm doing. I'm doing it purely combinatorially.
Yeah.
And I expect there's some rough equivalence in there. I don't know what it is.
Well, it will be combinatoric when we do it everything. When we do everything with path counting and.
But once you do the combinatorics, if you do it the way I do it, which is idiosyncratic and strange, you get the right answer. The right answer in the sense that it is consistent with the experiment, as I interpret it. And that's where I get the 130 GeV T-quark mass, which I think is realistic. And I had that as a prediction, which is why when they showed those green peaks, I thought, oh wow, they have a peak right where I say.
Yeah.
And this is really great.
Yeah.
But the problem was, Fermilab people hated that value because it was the value that had been observed by Dalitz and Goldstein using data given him by Chris Lee of Fermilab. And their analysis showed 130 JeV, which is consistent with this, which is consistent with me. But politically, the Fermilab people hated the Dallas-Goldstein people because they were not Fermilab. So anyway, I just put this as a little summary thing of what we've said over and over again too many times. E8 contains 120-dimensional D8. You take D8 out, you get 64 plus 64 fermion particles and antiparticles. You take D8 and cut out the two D4s, you get space-time 8 position times 8 momentum. And if you look at each D4 is 28-dimensional, and one has a standard model 12 gauge bosons with 16 ghosts, and the other has 16 gauge bosons with 12 standard model ghosts. So the function of ghosts in my model is to link the two pieces of D4, or in fact, link the two 600 cells that make up the Wittig polytope of E8. So anyway, this is just a little bit more detail about the D4 and the standard model and the stuff I've just said. Same thing with conformal gravity and standard model ghosts. Now, this is one of the pictures from Young's book, which to me indicates how you have the gauge bosons and the ghosts from the standard model and the gauge bosons and the ghosts from the other one. This is like the gauge bosons are the reds and the blue and green are the ghosts that do the hooking together. That may be a reach, but I think it looks reasonable to me. But it's not as straightforward as the other things. To me it is, but I know everybody else will say no. That's so. And this is details of how to do the calculations, exactly what is the mathematical formula for the masses. That is an interesting story. I won't try to do all the details here. But back around 1960s and 1970, Armand Wheeler, who was at Zurich, realized that these Schwinger sources that I talked about, little balls of 10 to the 27 particles, that if you have those things, if they were the particles, what determines what they do is their Green's function. And the Green's function is related to the geometry of these little Schwinger source particles. And Wheeler knew the geometry for electromagnetism, so he knew the Green's function for electromagnetism, and therefore he used that to calculate. He knew about gravity also, and he used that, therefore, to calculate the relative strength of electromagnetism, which is the fine structure constant, 1 over 137.03608, when you multiply it all out. But then after the standard model was done, after Wheeler had been sent to an insane asylum for his crazy idea in Zurich, he was never heard from again. But when you had the standard model come out, you had gauge groups that corresponded to Green's functions for each of the manifolds that correspond to the four forces. And Joseph Wolff had classified those four forces, the geometry of those four forces, years ago. So if you took the geometry that had been done for the color force, the weak force, as well as electromagnetism, then you can calculate their strengths too. And you do the same thing Wheeler did, and you wind up with realistic answers. And that shows it's very sad that when Wheeler was at the Institute for Advanced Study, he did not express himself clearly enough to make his views known to the people there. They dismissed him, and he went back to Zurich to the insane asylum. And that leaves you with the overall structure here. Now that we've broken everything down and done everything, we still have three generations of particles. That's three sets of 128 here, three generations. And we have still the D4 that goes with the Standard Model, and we have the D4 that goes with conformal gravity and dark energy, and we have the Higgs that was created when the space-time was broken from 8 to 4 dimensions. And you notice we reduced the integral to an integral over M4 Minkowski space-time, not 8-dimensional integral anymore. Now the Higgs that gets created ties into fermion particle-antiparticle pairs. And a Japanese, Yamawaki, and his co-workers have shown how that works with respect to Nambu-Jono-Leucinio models. And basically what happens is the T quark is so much heavier than all the other fermions that if you have really democratically all fermion-antifermion pairs, you would be democratic up in the massless region. But down here in the massive region, it's not democratic at all because all the mass belongs to the truth quark. And the truth quark and antiquark combine to condense in a Nambu-Jono-Leucinio model to match the Higgs. And that's what produces this Higgs truth quark condensate system that produces the three mass states. And the calculation of the three mass states was mostly done by Yamawaki and his co-workers in Japan. So that's basically, these are then the numerical results that I get from doing Wheeler-type work and then some combinatorics, but mostly Wheeler-type work. And I should mention that the actual volumes that Wheeler used, he didn't calculate them. They were calculated by Lu Qinghua, a Chinese mathematician who always called himself a janitor because that's how he started out. Just like in, what was the movie with Matt Damon?
Oh,
Good Will Hunting.
Was that it? Yes, yes.
Yeah,
So.
Good Will Hunting. So that's exactly how Lu Qinghua started. He started as a janitor and learned the math, and he became the best professor ever. Came to the U.S., didn't want to go to Princeton because he thought C.L. Siegel, who was already there, would steal his ideas and work, because Siegel was not as advanced as Hua. So Hua went to Illinois, but then the McCarthy era came in, and Senator McCarthy didn't like people from China because they were red communists. So Hua went back to China to be safe. And as soon as he got there, the Cultural Revolution began. And since he was a professor, he was elitist, and therefore he was sent for re-education in the farms.
Terrible life, yeah.
And he used his math to show them how to irrigate, so his farms did better than anybody else's. So they liked him, but he still had to stand for re-education in the town square every day. And every day he would stand there and be insulted for being elitist, and he said he would just close his eyes and think mathematics. So anyway, he is responsible for the numbers. He did all the volume calculations. And now that I've done that, I want to say how it filters down to the lower dimensions. This is E8, shown as a round representation. 8 circles, 30 dots per circle, 120 orange dots, 120 yellow dots. And one of the yellow dots would be the gravity ones. The orange dots would be the standard model ones. And therefore they split into 2 different 600 cells. The 120 orange become one 600 cell, 120 yellow become another one. And each of these 600 cells is called an H4 symmetry thing. And if you look at how they're built, each one is built out of a 24 cell and its dual. 24 cells and their duals, it's 24 cell self-dual. This may not look much like that, but it actually transformed directly one into the other. And there are 2 representations of the 24 cell. If you take the 24 vertices of this 24 cell, and the 96 vertices that are at golden ratio points on each edge of this 24 cell. These 96 plus those 24 give you the 120. And that ties into getting smaller, which we're trying to go down now. I am. F4 is just its root vector. These 24 plus 24 are the 48 root vectors of F4. And F4 then has two 24 cells. If you just look at one of the 24 cells, getting smaller again, you wind up with the D4, just like we talked about D4 before. We had a D4 for gravity and a D4 for standard model. But the D4 root vector diagram is just 24 points. It arranges a 24 cell. If you go down one more to D3, which is equal to A3, you wind up with a cuboctahedral thing. You'll notice that the cuboctahedral central figure, the green things of this representation of the 24 cell. So if you pull that green thing out, you go down from D4 to D3, which is equal to A3. And then you can go one more step down to H3. And H3 is based on the icosahedron. This is where we're beginning to get into the quasicrystals. And at H3 we see the quasicrystals emerge. You could call H4 a quasicrystal, but it's really sort of big for that because it's a complete thing. But if you want just a little quasicrystal inside a space, 3D space, you go to the icosahedron, and you got from the cuboctahedron to the icosahedron by a jitterbug transformation. So what I do is take this thing, jitterbug it, and you get down to the H3. But then going down to 2 dimensions, you go down to H2. And H2 is the Penrose star tiling, which is basically a non-crystallographic Coxeter group that's related to the A4 Coxeter group, but not the same thing. It lives within it. And here is where you get to the pictures that we were talking about earlier, the Penrose tiling. This is a Penrose tiling, and they have the 5 pie-shaped wedges around the origin. And then if you go down, you see what makes up the pie-shaped wedges. The particles, antiparticles in space-time. And things that fit in with them, connectors and things like that, and the little cyan things that some people call gravitons, but I call Bohm quantum quanta. And once you see this, you see these things start working in a fractal way, very much, and it's sort of like cellular automata. And the cellular automata, they're in 2 dimensions, and I'm still in 2D. In 2D, there are 256 basic cellular automata. Stephen Wolfram proved that back when he was at Oxford. But anyhow, these are all the things. They fall down into the graded structure of the Clifford algebra. 1, 8, 28, 56, 70, 56, 28, 8, and 1. And you can see how they even look like what they are. The cuboctahedron of the color force is represented by 8 things. You have the 2 in the middle and the 3 on the side.
Yeah, the eightfold way.
Yeah, exactly. And then you see similar things for gravity and the standard model. You see also a primitive idempotent looks like this, and that means that spinors look like this, and so forth and so on. This is the eightfold way, which is the star. This is, I'm sorry, I called it the cuboctahedron. The cuboctahedron goes with the conformal gravity. but they actually match up with the little patterns that are in here, and it's really kind of nice that they do. So that makes me think that there's some connection that I don't fully understand between the Standard Model, gravity, and said one and two-dimensional fundamental elementary cellular automata. And all this stops at the Octonians, because when you go beyond Octonians, you hit Sedenians and you have zero divisors. And zero divisors begin to look like G2, and I'm not going to go more than just say that, but I do want to say it, that there's a reason for stopping where we stopped at Octonian structures, because if you go beyond that, you get zero divisors, which don't seem to be physically realistic for what we want. And that's consistent with Jeffrey Dixon and Cole Fury, who base their physics on division algebras.
Yeah.
Then, how long has this been known? I think it's been known a long time, because if you look at the Great Pyramid has courses. And if you count the number of courses and give a number for the ways down to the basement, and you give a thing up at the top that isn't there anymore, you get the exact numbers that match the Clifford 8 Clifford algebra. So my view is that the guys that built the pyramids knew about Clifford algebras.
Well, it's certainly there's a lot of impressive engineering involved, which we still don't understand how it was
And-
done. There's no doubt about that.
And you have all sorts of very interesting things there. And one of the interesting things is, if you look at the way the pyramids are designed, if you stand here, look at the Sphinx, and point at the sun at the equinox sun will set right over the Sphinx's head. To the right will be the Great Pyramid, which has the Clifford algebra inside it. It is based on phi geometry. And to the left is the other big pyramid, which doesn't have internal structure, but is built not off of phi structure, but off of the 3, 4, 5 right triangles. The 3, 4, 5 right triangle angles give you that. The phi gives you that. 3, 4, 5 right triangles, if you map them out, give you U1, SU2, and SU3. So this guy corresponds to the Standard Model. This guy corresponds to gravity. They combine together at the Sphinx to give you the Clifford 16 and the full E8, which goes to show they knew even more. And just to get a little bit more so.
Well, that's interesting because
Yeah. What?
I'm just looking up I was looking at the Weinberg angle
Uh-huh.
from some kind of geometry like this once, many years ago, but I don't quite remember how it went, so I'm looking it up. Yeah.
So anyway, what I've done here is say this is like F4, this is like F4, and they combine to produce E8. That's because F4 lives inside Clifford 8 and has 256 of its elements. I'm sorry, it's 52 of its 256 elements. And if you consider the microtubules of the human brain and how they work and design it like that, you say, okay, here the tubulin here corresponds to Clifford 8. Clifford 8, you do a tensor product, and you wind up with a big thing that is the full microtubule, which has the Clifford 6 is Clifford 16, containing 248-dimensional E8 and a whole bunch of other stuff that can be used to convey information when you think. In other words, this thing is telling you how your mind actually works. And it is connecting it to the universe, like the way they thought. And if you work as we're doing in bounded complex domains, you have the bulk volume and you have the Sheloff boundaries. And the Sheloff boundaries are the boundary. That's where the physical things reside. In in the 8-dimensional space, it's RP1 cross S7, And if you just look at the Minkowski part, it's RP1 cross S2, which is a Lie sphere. And the Lie spheres are the space that we directly perceive. But the bulk inside the Lie sphere is the Lie ball, which is bulk complex thing where the complex numbers become effective. And if you say that this abstract stuff can live inside the Lie ball with complex imaginary structure, and that we live here in the Sheloff boundary with our microtubules and stuff, there is an exact correspondence between the 65,000 tubulins in a nice big microtubule in your brain and the 65,000 dimensions of Clifford 16. So there should be an exact copy of your state of mind inside this complex space. Therefore, if you saw the movie Lucy, you know she said we never die. And that's why you never die, because an exact copy of you is going to live in that book forever. And the whole universe will have a universal consciousness, which can be tapped into by Jung when he goes into his meditative trance or whatever it is in 1913. So it's basically the human brain is tied into the universe through all this stuff. And that's all there is to say. That's all, folks, just like Porky Pig.